So we'll get a little more in detail about how we implement a file system, right? So as we mentioned, we have the application view and the hardware view. So what the OS does is that it kind of has a series of steps where it essentially links the application perspective with that of the hardware, right? So from the application, the only way to access the file system is through system calls. This is what we have seen. And but internally in the OS, you could essentially split it into various parts. So we have the logical file system, which receives the system calls. So your functions such as sys underscore open or sys underscore read or sys underscore write would be part of the logical file system. So this is the region which essentially manages the directory structure, the file metadata information, inodes, and so on. So the next layer is the file organization module, which essentially translates the logical view of the a logical view of the file, that is the one-dimensional array, to that of the physical view. So for example, with respect to the hard disk, we would convert the logical address to the corresponding cylinders, track, head number, and so on. So the advantage you get in this way is that if there is a different secondary storage device, for example, an SD card or a USB drive, it is this specific layer which gets modified, and of course the layers below it. The logical file system would remain intact. The basic file system, which is the third layer, performs the generic read and writes to the devices. It also holds the buffers, the caches, and so on. So we have now established how to physically address a particular secondary storage device, for example, a hard disk through the cylinders, tracks, and heads, addresses, and so on. And the basic file system would now use these addressing modes to read and write to specific areas or regions in the secondary storage devices. So it would also hold aspects such as buffers, caches, and so on, which are present here, which essentially caches certain blocks of data, very similar to the cache that we find in processors, but these caches are essentially present in the DRAM, which is far more faster compared to the hard disk. So notice that the DRAM are based on capacitance and therefore electrical or electronic devices, and reading and writing to a DRAM is significantly more faster than to the hard disk, which are predominantly mechanical devices. The lowest layer is the I/O control. So this is where the access to the memory mapped I/O memory map region for the hard disk is performed. This is also the region where which controls the interrupts from the hard disk. It also configures the direct memory access, that is a DMA, all which is essentially done with this. So the lowest layer in this in this file system sequence is the I/O control, right? So what we see over here is that from an application perspective, things are very fixed. It's very much independent of what secondary storage device is utilized. However, as we go lower down in this hierarchy, the modules essentially become more customized to the type of secondary storage device, right? So for example, here at the file organization module, you would be able to distinguish between a hard disk versus a USB drive versus a SD card versus a CD-ROM. But when we go further down at the I/O control, you are now able to distinguish between various types of a particular form of secondary storage. For example, you would be able to distinguish between different CD-ROMs, whether it's a read-write CD-ROM, whether the CD-ROM is from company A or company B. Similarly, you'd be able to distinguish between different types of hard disk, say a hard disk from organization A or the organization B, the size of the hard disk, and so on. and the various features that are actually present, which is very, very specific to the type of device that is used, right? So this is essentially managed right at the bottom through the device drivers. On the file system, we have various contents that are present on the disk. An important aspect is the boot control block, which is present per volume, one per volume. If there is no operating system loaded onto a particular hard disk or a hard disk partition, then the boot sector block is essentially left empty. Then we also have the volume control block present in the disk. The volume control block essentially specifies the number of blocks in the partition, the size of the blocks, the free blocks, and so on. The volume control block is sometimes called the super block. Third, we have also present on the hard disk is the directory structure. So this structure essentially organizes files in in Linux machines or Unix machines. These may include file names and associated inode numbers. In Windows, it is a table. So we'll get to more about how this structure is organized in Linux and Windows shortly. On a per file basis, we also have the file control block. So the file control block essentially comprises of metadata about a file. It has a unique identifier that is associated with a specific directory, right? So besides what is present within the disk, the file system also has a component that is present in as part of the operating system as well, right? So this is the in-memory contents. So notice the difference, right? So we are looking at two aspects of the file system. So certain aspects are actually stored in the disk, while these aspects are essentially stored in the memory, right, and directly controlled by the by the OS. So the in-memory contents comprise of the mount table. Essentially, it comprises of the partitions, the secondary storage devices which are currently mounted on your Linux system with the help of this command like cat/etc/fstab. You'd be able to essentially look at the mounted file system, mounted directories and volumes that are essentially present. So as part of the in-memory contents, one would also have the system-wide open file tables that we have actually discussed. We also have the per process open file tables, that is one per process stored in the process control block. And we also have buffer caches, as we have discussed, which essentially buffers or caches the data in memory before it is essentially written back to the hard disk. Okay, so yeah, one critical aspect from a hard disk perspective is essentially to be able to use the available resources efficiently. So as we discussed with respect to the hard disk, we have multiple platters. Platters are divided into tracks, and tracks are split into sectors. The sectors form the basic block which is addressable. Now, in order to utilize the hard disk in the best way, we need to be able to identify which of these blocks or the sectors are utilized, which are not being utilized, and so on. So it's very important from the OS perspective to be able to track this free space in a secondary storage device, right? So this is important for two reasons. First, we would want to be able to efficiently utilize the available resources, and also it has an impact on the time taken to read and write or access a particular file, which may be associated with how the file is stored on the secondary device. Third, it also affects aspects in case the file system crashes or the hard disk crashes as to whether a particular file can be retrieved or not. So one of the easiest ways to essentially keep track of free space or free sectors or free blocks in a secondary storage device is by using a bitmap of blocks. So a value of 1 stored in a bitmap indicates that the corresponding block is essentially utilized by a particular file. If it is 0 in that bitmap, then the corresponding block is essentially free and can be allocated for storage. Right. Another way to keep track of this free space is by the linked list of free blocks. Right, and each of these have their own advantages and disadvantages. So now that we have we know we are able to identify within a secondary storage device which of these blocks are utilized, which are not utilized, and which are not utilized. We would now want to understand how to allocate blocks for a particular file. Right. So our idea is that we have a user who's running a program and wants to essentially store a file in the hard disk. Now the operating system essentially understands which files are used, which blocks within the hard disk are used, which blocks are essentially free, and it wants to essentially best use the resources available in the hard disk to store this file. So there are various different methodologies that have been proposed for allocating blocks within a disk for the OS. So one is called the contiguous allocation, the other is the linked and allocation, and the third is the indexed allocation. Right. While a variation of the indexed allocation is used in Linux systems, the linked allocation is typically used in a Windows-based system. The easiest and the simplest one is the contiguous allocation. So we'll start with contiguous allocation and slowly build up to the linked and the indexed allocation methods. So what is the contiguous allocation? Right. So what we have right now is an abstract view. So where we have different blocks. So each block could be, say, of 512 bytes or 1 kilobyte or so on, some block size. And what we need to do is essentially use these blocks to store certain files. Right. Now let us say that our directory structure looks like this. We have 3 files: move, snow, and fall. Right. And the amount of space that each of these files requires in terms of blocks is 3, 7, and 4 respectively. Right. Now our objective is to allocate space on the hard disk or in the secondary storage device for these 3 files, move, snow, and fall. Right. So the easiest way is that we create a directory. So within the directory, we set the 3 files, move, snow, and fall. We essentially use a contiguous allocation, which means that all the entire file is essentially in contiguous locations. So for example, move, the file move starts at the block number 5, which is this block. This is the 5th block, and since it is of length 3, so it spreads over 3 blocks, 5, 6, and 7. Right. So so what we see over here is that it is essentially contiguous, and the entire file is essentially in contiguous blocks. The advantage of this is that it's the simplest, and quite often this could also be the fastest means for allocation, because there's for essentially reading out the particular file, because it's very simple to identify where the entire file is essentially stored. Right. The other example is snow, the file snow, which is blue. So it starts from the block 22. So this is 22 and extends for 7 blocks. So 22, 23, 24, 25, 26, 27, and 28. Right. So 22 to 28 is where snow resides. And you also have the third file, fall, which starts from the 12th and is of length 4, so occupies 4 blocks. Right. So so the directory essentially keeps track of where the file starts, right, and also the length of the file. So very, very simple. So the allocation that is done is typically the first or the best fit. Right. So what do you mean by the first fit or the best fit? Right. So when the OS wants to allocate a file to a particular directory, so it would and let us say the directory is, say, X, requires X blocks. the OS would essentially in the first fit allocation look into these into the free blocks and identify the first set of free blocks which is at least of x blocks, um, and this would be essentially allocated. The best fit, on the other hand, is where the OS looks at all the blocks that are present and identifies the ideal location the where the given file would exactly fit in, right, with such that it leaves very less space vacant. Okay, there are lots of disadvantages with this form of contiguous allocation, and as one would be obvious. So one aspect is the external fragmentation. So external fragmentation would occur when there is when there are when there are sufficient number of blocks that are free, but they are fragmented across the disk, right? So so these, if accumulated together or if placed together, could actually service or be able to use to store files. But since they are spread across the directory, they cannot be used in a contiguous manner, right? So very often when in such cases we would have to use defragmentation techniques. So what defragmentation techniques do is that they move files closer together such that the all the unused blocks are placed together. So this essentially removes the fragmentation or reduces the amount of fragmentation that is present and makes the space of the disk much more usable. But the limitation, of course, is that this defragmentation would need to be done periodically. It could take quite a lot of time depending on the size of the hard disk present. The other thing is that in many cases users would need to specify the maximum file size at creation, right? So why is this required? So this is required if you want, in many cases, if you want to prevent this fragmentation. But it could also result in internal fragmentation, where a file may be much smaller compared to the amount of space that is requested. So it's very difficult to identify and detect such internal fragmentation cases. The second methodology is uses a linked list allocation. So here, instead of storing the entire file in contiguous blocks, what we essentially store in the directory is the start block and the end block, right? So for example, here the file move starts at block 5 and ends at block 1. Along with the data that is essentially stored in the file, it would also contain a pointer to where the next block is present, right? So move starts at 5, it has a pointer to the 12th block, which indicates that the second block for move is present in the 12th is present in the 12th block, and the third block is essentially present in block number 1, right? So similarly for snow, we have the first block present in 30, and we have pointers in each case which show us where consecutive blocks are present, and similarly for fall. So what we see over here is that the aspect of fragmentation is taken care of very efficiently, because we don't have such contiguous allocation. So this completely solves the problem of external fragmentation. However, this form of linked allocation has its own limitations. First, it's not suited for direct access to of all files. Every file needs to be accessed through pointers, which means that pointers need to be stored in each block. So each block would contain some special area which needs to store pointers, and this may create overheads. There are various techniques to reduce the overheads, but these overheads cannot be eliminated. The other limitation is that if one of these blocks gets damaged or one of these pointers gets damaged, then it would essentially prevent or make it difficult to retrieve the rest of the file. So what do we mean by this? So consider this this file 30, which rather consider this file called snow, which starts at the block number 30 and then has a pointer to the next block here, and so on, right? The third block is present here, and so on. So let us say that due to some reason this particular block gets damaged, right, and cannot be accessed. What it also means is that you have actually lost the pointer, the subsequent pointer, because the block is not damaged. The pointer is essentially stored as part of the block, which means that the rest of the file cannot be essentially accessed. So it means that for this particular case, we are restricted to only two blocks. The remaining blocks is not easily retrievable. Another limitation which is also of a similar nature is when there is a bug in the operating system, and due to some reason a pointer value is essentially changed, right? So we have a pointer, let us say if I take the fall example, so I have a pointer which is essentially say present here, and due to some reason this pointer has got corrupted, or there's a bug due to which the pointer is corrupted, and it can now be point to an arbitrary location, say points to the 12th block, which essentially has the contents of move. So such issues may essentially crop up. An alternate way to actually handle this situation is by using the FAT file allocation system. So the FAT file allocation system was invented by Mark McDonald and Bill Gates. Here the idea is very simple, that instead of storing the pointers with each block, you essentially have a file allocation table where you essentially store the pointers. So now you have a directory structure with your move, snow and fall, and with each of these files you also have the starting block. So move starts from 5, and here is your file allocation table. So at the 5th block, which is this, you have an entry called 12, which essentially means that the second block for move is at the 12th index in the file allocation table, right? So this is the 12th index. It has an entry 1, which means that the third block in move essentially is is in block number 1, right? So in block number 1 we have EOF, which essentially denotes the end of file. So what the operating system would do is that it would look into the directory structure. It would see the starting block for 5. It would see the starting block for move, which is 5. It would look into the file allocation table to obtain the next block. Subsequently, it would essentially look into the block 5 and read the contents of that block. The file allocation table essentially has 12, which indicates block number 12 has the next block for move, so which is this, and this is red. The third block is at block number 1, so the block number 1 is red, and this is also the end of file. So in this way, what we are actually doing is that we are eliminating or disconnecting the pointers from the actual blocks and storing the pointers in a special table called the file allocation table. So the FAT table, or the file allocation table, is a table that contains one entry for each block and is indexed by the block number. Files represented by linking pointers in the FAT table, right? So implicitly your each entry in the file allocation table essentially links to a subsequent entry, right? So how does this essentially help? So since pointers are not directly stored within the blocks, there is essentially greater reliability, because for instance the file allocation table can be duplicated. It's relatively small compared to duplicating the entire block. We just need to duplicate the file allocation table, and therefore in many cases even if let us say one block essentially is not readable, the other blocks, in this case block number 5 and block number 1, would continue to be read. So the amount of information that is lost due to a invalid block or a corrupted block is essentially kept as small as possible. It also solves the problem of direct access, which is present in linked allocation, and it can be easily used to grow files. So if I want to increase the size of move, so all I need to do is replace this end of file with, let us say, 3, right, which means that the next block would be present in block number 3, right. So the disadvantage, however, is that the volume size or the size of the entire space occupied is often determined by the file allocation table size. So this is the reason that the file allocation table, if it is fixed, it will essentially determine what is the maximum size for, or what is the maximum number of blocks that can be present. The alternate approach is known as the indexed approach, and variants of this is essentially used in Linux based systems. Here the idea is that the directory essentially has the file name and a pointer to an index block. So here, for example, we have the index block is 19, which is essentially this particular block present, and within this particular block we now have a sequence of block numbers 9, 16, 1, 10, 25 and so on, right. So what it means is that the first block of this file Jeep is present in block number 9, that is this one. The second block is present in block number 16. The third block is present over here in block number 1. Fourth block is in block number 10 and so on, right. So what we are actually doing here is, rather than having a separate file allocation table, we are using one block as the index block, and this block essentially contains a sequence of numbers of block numbers, which are used to point to the various parts of the file, right. So the question needs to be asked is, how large should the index block be? So one thing you would actually observe is that the maximum size of the file would be determined by the number of entries present in the index block. So if the size of the index block is small, that it would only indicate that the maximum size of the file is limited, right. So a way to tackle this issue is by the aspect of multi-level indexing, where we have multiple levels of index tables, which eventually point to different data blocks. So this is an example of the Linux ext2 and ext3 file system, which essentially uses this multi-level indexing scheme. xv6 also, which we will actually see later, uses a similar kind of scheme. So here is where we have an index block, and what is essentially present here is various aspects about the file, such as the owner, the time of creation, the number of blocks, and so on. But important for us are these index pointers. So you have direct blocks, which essentially mean that each entry in these blocks directly point to corresponding data. The other alternative is this single index, where we essentially have the blocks pointing to the data, or rather we have these blocks pointing to another block, which essentially holds addresses or block numbers, which then hold the data. So we have a single level of indexing. In a similar way, we have double indexing as well as triple indirect indexing as well. So how are these blocks essentially useful? So for small files, we would typically want to use these direct blocks, because it's only one level of indexing that is required. You just look into this main table and then obtain the pointer to the various blocks to essentially read out the data. But we go for double or triple indirect addressing for large files. So using this, we are able to address a large or create large files which is not possible with these direct blocks.